Welcome to homework.
Hello everyone, today we're doing chapter 14, problem 50, and this question asks us to determine how many carbon NMR signals does each of these following compounds show. So, like before, we know how to do this. We know how that each peak or each signal in H NMR or carbon NMR is from a chemically distinct carbon that exists in its unique chemical microenvironment. So, we know that something like this has one carbon here that's bound to a hydrogen, bound to three carbons, and then we have three carbons here. Each of these three carbons is bound to three hydrogens and one carbon. So because these three carbons, these three methyl groups here are bound to the same substituents, we can say that these are all going to be the same type of carbons. Then we have this carbon down here, that the central carbon that's bound to a hydrogen and three carbons. So we're going to have two types of carbon signals in this molecule. So what about this molecule here? Well, we see that we have a carbon here that's bound to three hydrogens and one carbon. We have the central carbon that's bound to four carbons. These two methyl carbons are bound to three hydrogens and one central carbon here. We have an CH2 here, and a CH3 here. So right off the bat, we know that these two carbons are the same. They're bound to three hydrogens, and they're bound to the same central carbon atom down here. So we have one type there. And then we know that this terminal carbon here is bound to three hydrogens and one carbon. This one carbon is bound to those two methyl groups and is bound to another R group. So we have another type of carbon here. Obviously, the central carbon here is very unique because it's the only carbon that's bound to four non-hydrogen substituents. So I'll actually do that a different color. We have this one here. But in essence, what we can actually determine is that this blue carbon being bound to three protons and this central carbon here, well, like, what's the difference between this blue one and this green one? So there's actually no difference between them. So these green carbons are actually these three carbons here, because each of these three carbons are bound to three protons and the central carbon atom in the middle. So these three carbons are all one type. Then we have this central carbon that's one type. Then we have each of these CH2s that are one type, because this CH2 is adjacent to a carbon that's bound to four non-carbon substituents, while the CH2 is bound to a terminal methyl. So then we have one type, these three carbons that are these green carbons, 1, 2, 3, 4, 5. So we have five chemically distinct carbon signals here. What about for this example here? So I always like to draw it out if it's given in this sort of formula form, just so I could very easily distinguish everything. And here we see that we have this terminal carbon here that's adjacent to an oxygen. So we have one carbon type here. We have the central carbon that's bound to two carbons, one oxygen, one hydrogen. So we have a second type of carbon here. And we have these two methyl carbons that they're bound to three hydrogens and the central carbon atom. So these are the same type. So here we have three types of carbons. And for D, if you see right off the bat, like, we can start with the simplest one, that being the carbonyl carbon. That's this unique carbon environment because of the double bond to oxygen. Then we have the terminal carbons, which are this carbon here. This carbon is bound to three hydrogens and one carbon here. This carbon is bound to two hydrogens, one methyl carbon, one carbonyl carbon, so that's unique. This carbon here is bound to a CH2 and then a carbonyl carbon. This carbon here is bound to CH2, CH2. And this carbon here is bound to CH3, CH2. Then we have our terminal carbon that is unique from this terminal carbon because this green carbon is only 2 carbons away from the carbonyl carbon, while this red carbon is 1, 2, 3, 4 carbons away from the carbonyl carbon. So in essence, we have 1, 2, 3, 4, 5, 6, 7 types of carbons in this molecule. Essentially, because there's no internal plane of symmetry, each of these carbons will be unique. So what about this molecule here? Well, this molecule actually has an internal plane of symmetry. So remember, what is true on one side will be true on the other side. So all the type of carbons on one side will find the same types on the right side. So right now we have an alkene carbon on the left, so we'll have that same alkene carbon on the right. Then we have this CH2 carbon that's bound to a methyl group and the alkene carbon, and we have that same CH2 group on the right. Then we have our terminal carbon group here, which is present on both sides. So we have 1, 2, 3, and the same 3 types of carbons on the right side as well. So we have 3 types of carbons in this problem here. So what about this one? So once again, there's no real internal plane of symmetry. This carbon is directly bounded to this electronegative oxygen atom, while this carbon next to it is 2 carbons away. This one is 3, 4, 5, 6, 7. So we can determine that each of these carbons being 1 extra carbon away from this electronegative group will be in this unique chemical environment. So we can say that we have 7 signals here for the 7 carbons present in this molecule. What about for G? Well, G, we see that there's an internal plane of symmetry. So remember, what happens on one side is true for the other side. So we have this alkene carbon, this terminal alkene carbon here, which is going to be unique from this alkene carbon here bound to 2 carbons. And then we have, following it on the one side, we have this CH2 that's bound to this alkene carbon, another CH2, and we'll have that same type of carbon on the other side. And then we have this carbon here that's bound to CH2, CH2, and that carbon is also found on the other side. Then we have our carbon that's on the internal plane of symmetry, which is unique from any other carbon. So in essence, we have 1, 2, 3, 4, 5 unique carbon types here. Using the same logic, the same is true for this molecule here. We have this carbonyl carbon, this ketone carbon, the carbons that are right adjacent to it, then we have the carbons that are 2 carbons away from it, and then we have the single carbon that is 3 carbons away from the carbonyl carbon, making these 1, 2, 3, 4 carbons all in a unique type of environment. In this molecule, once again, we have internal plane symmetry, but this time it goes like this. And we have these alkene carbons here, cycloalkene carbons here, which are the same type on either side of the internal plane symmetry, the carbons that are alpha to it, and then the carbons that are beta to it. So we have 3 types of carbons in the last problem here.